Hello students, I expect that you are doing well. Today we're going to perform a simulation using SOLIDWORKS Flow Simulation, and what we are going to model is a heat exchanger that is used in a microelectronic system. In this case we are calling this MEMS heat exchanger, and as I told you before, we are using SOLIDWORKS Flow Simulation. Okay, the description of the problem is the following. We have this example that we have taken from the COMSOL application gallery, and we have adapted it to SOLIDWORKS Flow Simulation. This example is used to specify a conduction and convection heat transfer model using SOLIDWORKS Flow Simulation, and the main objective of this tutorial is to model a stainless steel heat exchanger using SOLIDWORKS Flow Simulation to determine the operation temperatures at the heat transfer from one fluid to another. The 3D model in this case involves heat transfer through both convection and conduction mechanism. Okay, the geometry that we are going to use is the one that you are seeing in your screen, and it mainly consists of a unit cell. In this case, what we want to model is a heat exchanger that is countercurrent flow, but we have we have many tubes in this case in this bar. But it is not necessary to model the entire bar or the entire heat exchanger. We just need to identify what is the unit cell in this case, and we can determine that this is the shape or the geometry for a unit cell. This unit cell is repeated throughout the length of this heat exchanger, and we only need to model this or specify this in SOLIDWORKS Flow Simulation. We are doing this, or we can do this in order to save computational costs or to decrease the size of the computational domain. Okay, what we want to determine for this example is we have to determine the outlet temperatures of every current, in this case the cold and the hot sides, and later we want to determine what is the heat rate that is transferred and received by both fluids. Finally, we want to determine what is the average heat transfer coefficient both in the cold and the hot sides. We are given with the size of the geometry that you are going to have in the next slide, and we know that the material of the solid can be specified as a stainless steel 302. We have to determine the inlet temperatures for every current. In this case, for the hot side, it is equal to 330 Kelvin, and the maximum velocity it is 50 millimeters per second. We must know that in micro devices or microelectronic systems, we are dealing with laminar flow or laminar regime flow. For the other side, for the cold side of this heat exchanger, we are given with a temperature for the inlet of 300 Kelvin, and the maximum velocity is going to be 50 millimeters per second. Okay, the geometric characteristics are given in these sketches. We are given that the depth of this device is going to be 400 micrometers, and the height is going to be 300 micrometers. The width is going to be 100 micrometers in this case. The diameter of every pipe is going to be 50 micrometers, and the distance from the center of the circles or the cylinders to the top side is going to be 100 micrometers. The outlet boundary conditions are going to be specified as the atmospheric pressure. Okay, as I told you before, the stainless steel is going to be the material that is going to be surrounding these pipes. Okay, for this simulation we are going to set the mesh size that is given by SOLIDWORKS. By default is given as level 3, but we can specify 4, 5, or 6 in this case, or even more if you want. the total amount of cells that are given for the default level 6 is going to be higher than 100,000 elements or cells for this computational domain. Okay, we have to highlight in this case that we are going to modify a little bit the computational domain respect to the one that is given by default from SOLIDWORKS Flow Simulation. In this case, as I was telling you, we are repeating this unit cell many times. So we are going to take into account that every side wall it is going to have a symmetry boundary condition. So we have to specify firstly in SOLIDWORKS Flow Simulation that this wall has a symmetry boundary condition and the other side has a symmetry boundary condition as well. At the end, we are going to have to determine what is the temperature, the heat rate, and the heat transfer coefficient for this system. In this case, we are showing some iso surfaces, and this is for both the temperature. The ones that are given inside the pipes are iso surfaces for the temperature, and the ones that are given inside the solid material are the heat flux iso surfaces. We are also going to obtain the flow trajectories in order to visualize what is happening inside the tube and in order to have a temperature profile inside the fluid materials. Later we have to determine what is the average heat transfer coefficient, but we also can determine what is the specific heat transfer coefficient in every point of these pipe walls. We know that the heat transfer coefficient is going to be determined according to the velocity of the fluid, according to the temperature of the fluid, and according to the temperature of the external wall, in this case the walls of the solid material. So we know that the heat transfer coefficient is going to be changing, but we can determine an average heat transfer coefficient. The average heat transfer coefficient are given in this slide, and we can see that we have values around 7,000 and 8,000 depending on the side of the fluid or the side of the heat exchanger. Later we also are going to determine what is the heat transfer rate, and we are calculating a heat transfer rate of 0.011 watts. The heat transfer that is transferred from the hot side to the cold side, and this is the heat transfer rate that is received by the cold side. And finally, we are going to estimate what are the outlet temperatures. We have here that this lower pipe is the one that is in which the hot fluid is flowing, and we know that the inlet temperature is 330 Kelvin. At the outlet we have a temperature of 312 Kelvin. For the cold side, we know that the fluid is entering at a temperature of 300 Kelvin, and the outlet cold fluid temperature is going to be about 313. Okay, as I told you before, we obtained this example from the COMSOL application gallery, and we adapted this example to SOLIDWORKS Flow Simulation. As you know, you can always refer to the SOLIDWORKS Flow Simulation technical reference in order to know more about the equations that are being solved in this software. Okay. We're going to move on to SOLIDWORKS Flow Simulation, to SOLIDWORKS, and there we can find the Flow Simulation component. I'm going to open SOLIDWORKS. I'm just waiting for it to load. Okay, we have this window that is the main window for SOLIDWORKS Flow Simulation, and I'm going to click here for a new document, and I'm going to select a new part. Okay, now we have this canvas or this workspace, and I'm going to select the front plane, and you will see that some squares will highlight in the workspace, and I'm going to begin working on the front plane. I'm going to click front plane from this side that is called Feature Manager Design Tree, and I'm going to select front plane. Later I'm going to click Sketch. We are going to have this box, and I'm going to click Sketch. Okay, I'm going to the menu bar, and I'm going to select the Sketch tab, and I will select corner rectangle. I will begin drawing a rectangle, and I will begin from the reference or the origin point. Okay, I'm going to make sure that we highlight this point, this orange point, and I'm going to drag my mouse in this form. Okay, I'm going to have this. You are not going to worry about the actual length at this moment, but later we can specify them with the Smart Dimension tool. You can find the Smart Dimension tool in the Sketch menu, and you can select Smart Dimension here in this zone. I'm going to click Close Dialog to close this window, and I'm going to sketch a Smart Dimension tool. Okay, here I'm going to specify the length, and I'm going to the presentation in order to remember what is the length that we have to specify, and we find that the width is going to be 100 micrometers. I'm going to write here 100, and I'm going to specify micrometers units in lowercase. Okay, I'm going to click OK, and it changed the size. I'm going to zoom in here, and later I'm going to specify again with the Smart Dimension tool the height of this device. That is going to be 300 micrometers. Okay, we have this. What we have to do next is to draw the circles or semicircles in this case that are going to represent the pipes or the tubes. So I'm going to I'm going to close this dialog, and I'm going to go to Sketch and select Center Point Arc. You will have 3 different options, and I will select the first one. So I'm going to position in this zone, the lower zone, and I'm going to start by the center point. Okay, and later I'm going to position here this second point, and I'm going to position the third point here. Make sure that you highlight the reference line in orange. Okay, I will have this, and I have to use the Smart Dimension in order to specify what is the actual length for this circle, semicircle. And we know that it's going to be 50 micrometers. 50 micrometers. And you're going to click OK. Later I have to specify what is the distance from this line, the bottom line, to the center of the circle. And you may know that this is going to be 100 micrometers. So I'm going to specify 100 micrometers and click Save. Okay. Okay, I'm going to close the dialog here, and I'm going to add a second semicircle or center point arc, and it's going to be similar. I'm going to draw a star by the center. Later I'm going to add the lower point, and finally the top point. Okay, I'm going to use the Smart Dimension function, and I'm going to specify this as 50 micrometers. Then click OK. Later the distance from the center of this arc to the top line is going to be 100 micrometers. Okay, now we have this to the sketch, this 2D sketch, and we have to make an extrusion in this case. If you want to visualize in isometric view, you are going to go to this view orientation button, and I'm going to click isometric. Okay, I'm going to zoom in here, and we will have something like this. Okay, now we have to extrude this in order to generate a 3D object from a 2D sketch, and I'm going to features in this case, and I'm going to select extruded boss base from the feature menu. Look for extruded boss base and click on it. Okay, we have to specify what is the depth. In this case is 400 micrometers for this heat exchanger, and we can specify here 400 micrometers. And we are required to specify what is the contour that we want to extrude. We can select different surfaces, and in this case we only want to select this surface. Okay, now in this way you can see that you will have a 3D object similar to this. I'm going to click OK, and now we're done with the geometry up to this point, but we still have to make some other changes. Okay, so in this case, remember that when we are dealing with an internal type of flow in SOLIDWORKS Flow Simulation, we have to specify leads, and the lead will have to be specified in this zone, but this zone is also open by this side, and we will have to add leads as well in this phase, but this is not going to be possible. We will need to create physical boundaries or physical walls in this zone. Okay, so in order to create leads for this inlet and outlet pipes, we are going to create a physical wall in this side. So what we are going to do is to make sure that we are out of any sketch, and we are going to begin drawing a sketch on this face. So I'm going to click here in any point, and I'm going to select a sketch from the box that pops up. Okay, I'm going to click sketch, and I'm going to select from the sketch menu the corner rectangle, and I'm going to make sure that I highlight this point. You can begin from any corner that you want, but I'm going to begin from here. Okay, I'm going to start drawing this rectangle, and you will have this shaded rectangle here. I'm going to click close dialog. If you activate the isometric view, you will see something like this, and I'm going to extrude this wall a little bit, and the value is going to be 5 micrometers for the thickness of this wall. Actually, we don't need this wall, just by the requirements of SOLIDWORKS Flow Simulation. Okay, so the thickness can be very, very thin. I'm going to features, I'm going to select extruded boss base, and I'm going to select here or specify what is the thickness for this wall, and it's going to be 5 micrometers. There you have. Okay, I'm going to click OK. Okay, I'm going to come back to this operation. I'm going to click on this node, and I'm going to edit feature, and here we have the option to merge the result. In merge result means that you are going to join or merge both solids that you already have. I'm going to deactivate it here, this option, and this will be separate solid bodies. Okay, this is going to be one body, and this is going to be another body. We are going to repeat the operation on the other side, so I'm going to make sure that we are out of any sketch. I'm going to rotate the view, and I'm going to position on this surface. So I'm going to click here. You are this box is going to pop up, and I'm going to select sketch. So we are going to repeat this. We are going to select corner rectangle. We are going to begin with from this origin point. Let's draw this rectangle. You are going to have this shaded surface, and you are going to go to features and extruded boss base. By default, it's going to recognize the thickness from the previous face, and it's going to recommend you to use this same thickness. So I'm going to deactivate the mesh result, a checkbox, and we will have something like this. I'm going to click OK. So now you have 3 separate bodies. That is going to be the wall by the left side, the wall from the right side, and the main block. Okay, so before anything else, you are going to save the work. I recommend you to save something, save everything in the same in a single folder. And I'm going to give it the name. Okay, now we're going to specify the flow simulation model. And to activate the flow simulation, remember that you have to go to SOLIDWORKS add-ins and look for SOLIDWORKS Flow Simulation. Another way in which you can activate this is going to this menu, the top bar, and in this little arrow you will select add-ins and look for the SOLIDWORKS Flow Simulation add-in. So here it is, and you're going to activate both checkbox. And OK. So you will have a new tab here that is called Flow Simulation, and we are going to create firstly the leads. Given that this is an internal type of flow, you will have to specify the leads, and this is going to tell the software that the fluid flow is going to be exclusively inside this cage or this geometry. So I'm going to go to Tools, Create Leads, and you have to select planar surfaces. In this case, you are going to select this surface, and it's going to recognize that you have holes here, and it's going to give leads for these holes. You are going to rotate the geometry, and you are going to select the another face. So you will have in total 4 leads. So click OK. Now you are done with your geometry. Now you can save your work before anything else, and now we can specify the flow simulation model. So we're going to wizard. Here in flow simulation, find the wizard, and the wizard is going to guide you through the main steps to specify your CFD model. So I'm going to I'm going to type MEMS here. MEMS means micro electromechanic systems. Next, here you can change the unit system that you want to work with, and if you want to change a specific unit, you can do it here for a given physical parameter. I'm not going to change anything, so I'm going to click Next. And you have to specify this analysis type. It can be internal or external. I'm going to set it as default for internal, and I'm going to activate the heat conduction in solids. In this case, I have the 2021 version of SOLIDWORKS. Maybe it's a little bit different in your version if you have a newer version. So you have to activate the heat conduction and the fluid flow. So here we have heat conduction in solids. I have to activate the gravity, but as you can see here in this arrow, the gravity is not specifying the right component, so I'm going to change the value of the gravity for the white component exclusively, and there we have, and that's all what we have to specify in this window. So click Next, and later I have to specify the fluid that we are dealing with. If you click directly add button, you will add water by default, but you can always find it in liquids, and it is given, well, it is not already here, but it's given here in this list. So you can specify here, if you already know that this is going to behave as laminar flow, you can specify laminar only. Or if you know that you are going to be dealing with turbulent flow, you can specify turbulent or laminar and turbulent. So I'm going to specify laminar only here, and I'm going to click next. Later we have to specify what is the solid material. I'm going to select from the alloys list, I'm going to select stainless steel 302 and next. Later you are asked to specify what are the wall boundary conditions. I'm not going to change anything. This is going to be the roughness, 0 micrometers, and this is regarding the wall thermal conditions. I'm going to click next. Later you have to specify the initial conditions for both the solid material and the velocity field. I'm going to click finish. I'm not going to change anything. We are given that the pressure, the reference pressure is going to be 1 atmosphere, that the initial temperature is going to be 293.2 Kelvin, and the fluid is not moving at the very beginning. So finish. Okay, you are going to have this computational domain. Maybe you cannot see it because it is inside the boundaries of this solid material. So I'm going to go to display, and I'm going to activate the transparency here in the flow simulation tab. So transparency, and set it to 100. Okay, I'm going to click on computational domain, and you will see that there is. Okay, I'm going to modify it a little bit, because remember that we want to define a symmetry condition on the side walls. Okay, this means that what is happening in one side of this geometry is happening the same in the other side. Okay, so we are going to have to modify a little bit the computational domain. So I'm going to click edit definition, and I'm going to position here. Here, size and conditions section, we are going to locate this boundary condition, and I'm going to give symmetry. Okay, and in this other section, in the X minimum, I'm going to select symmetry as well. But we have to define that this minimum value is going to be 0 meters, and the other value, the maximum X value is going to be 0.0001. Okay, now you will see that the computational domain for the symmetry condition is going to begin from 0. Okay, so it's going to begin here in the section that it is of interest for us. We are not considering inside the computational domain this wall here. So what is happening inside this solid, it is going to be happening in this symmetry region. And the same is going to be for the right side. Okay, so the actual computational domain is going to finish here in this gray shadow, and the symmetry condition is going to begin here. So the reason that we use this maximum X value, it is because we have a value of 100 micrometers in this length, or in this width. So, and that's all what we have to change for the computational domain. So I'm going to click OK. So I'm going to click view orientation, and I'm going to activate the isometric view. Now we have to specify what are the fluid subdomains. I'm going to right click on fluid subdomain. I'm going to click insert fluid subdomain, and I'm going to position on this tube, and I'm going to right click on it, select other, and I will have to locate this tube or this surface that is highlighted in orange. Okay, in my case it's the second option, and you will see that this tube is going to be highlighted in blue. So this is going to be the fluid subdomain for the cold fluid. So the cold fluid is going to have an initial temperature of 300 Kelvin, and the liquid or the fluid is going to be by default water that is already selected. If you had another fluid, you can add it here. So I think that's all what we have to specify there, and I'm going to click OK. I'm going to specify here that is a cold fluid. Later, I'm going to add a new fluid subdomain. I'm going to clear this box, this selection box, and I'm going to position on this tube, the lower tube, that is going to be the hot side. I'm going to right click on it, select other, and I'm going to look for the surface of the external surface of the tube, that is in this case the first one. Okay, now you can see that the tube is highlighted in blue, and I have to specify that the initial temperature is 330 Kelvin. Click OK. The solid materials. Okay, the solid material was already specified for the general model, but let's take for example that you have different solid domains or subdomains. You can specify every different domain with different solid materials here. So I'm going to right click solid materials, insert solid material, and I'm going to select this block. So this block is called Boss Extrude 1, and I'm going to look for the alloy that we selected, that is going to be stainless steel 302, and OK. Now we have to specify the boundary conditions. The boundary conditions, I'm going to right click here, insert boundary condition, and I'm going to specify this phase as the first inlet boundary condition for the hot fluid. I'm going to right click on lead 4, select other, and I'm going to select the first one. I'm going to go to the type section, and I'm going to select flow openings and change for inlet velocity. The inlet velocity, I think that was going to be 50 millimeters per second. Okay. This is going to be 0.05 meters per second, and I'm going to make sure that we have the temperature that we require. Okay, I'm going to expand the thermodynamic parameters part or section, and I can visualize here that the temperature is the one that we already require. Okay, that we already defined, I mean. Okay, I think that's all for this surface or this boundary condition, and I'm going to click OK. Okay, now you will see that you have this indication that we are specifying inlet boundary condition. So I'm going to specify here that is the inlet fluid, hot fluid. And I'm going to add a new boundary condition. I'm going to clear this selection, and I'm going to rotate the geometry in order to select what is the outlet for the hot fluid. This is going to be this side, and I'm going to change the type of boundary condition. In this case, it's going to be pressure openings and environment pressure, and that's all. Okay, now you can see that the arrows means that we have an outlet boundary condition that can, in other words, we have a pressure opening, and in this case the flow can be inwards or outwards. Now we are going to define the inlet cold temperature, insert boundary condition. I'm going to specify that in this lead number 1 we have a flow opening of inlet velocity type, and I'm going to select 0.05 meters per second. And thermodynamic parameters, you will see that the temperature is already specified as 300 Kelvin. And OK. Later, you have to specify, well, I'm going to specify the name, inlet cold temperature, and I'm going to add a new boundary condition. I'm going to clear the selection, and this is going to be this side, this lead 3. I'm going to select the type pressure opening, environment pressure, and OK. Now you're done with boundary conditions. I'm going to change the name for outlet cold fluid. This is going to be inlet cold fluid, and this is going to be outlet hot fluid. There you go. Okay, now we have to specify what is the mesh. I'm going to double click on global mesh. I'm going to set it to 6, and I'm going to show the basic mesh, and you will have a mesh similar to this. And OK. You can right click on global mesh in order to hide the basic mesh, and that's all. Okay. Now I think that you are done with this specification, so I'm going to save the work, and I'm going to run the simulation. You have to go to Flow Simulation, and I'm going to click Run. Make sure that you are selecting New Calculation, as it is the very first time that we run the simulation. This is going to be deactivated, but every time that you want to run it again, you will have to make sure that it's selected New Calculation. Okay, I'm going to click Run. You will have this window, and we're going to wait till it finishes the calculation. Okay, the calculation is already complete. I'm going to close this window, and I'm going to expand the results tab. So I'm going to create an isosurface in order to have a visualization of what is happening with the temperature inside the fluid subdomains. And I'm going to right click isosurfaces, insert, okay, it's not going to give me the opportunity to select the boundaries or the domains that we want to show, but it's going to allow me to select what is the parameter that I want to visualize. In this case, I want to visualize the temperature of the fluid, and I'm going to specify the number of levels or the number of isosurfaces that I want to see. The value is going to be between 300 Kelvin and 330 Kelvin. And I'm going to specify 50 levels. The appearance, I'm going to specify that I want to see the temperature of the fluid, and the transparency is going to be set as 0. So I'm going to click Preview, and we will have something like this. Okay. Now you can see that in the entrance of this side it's going to be almost 300 Kelvin as expected, and on the other side is going to be 330, and it's going to be changing the temperature along these tubes. Okay, we can let it as 50, or you can increase it if you want. Okay, I'm going to click OK. I'm going to click Save. And I'm going to add a second isosurface. I'm going to click here temperature, specify temperature of the fluid. And I'm going to add another one. In this case, it's going to be the heat flux. Okay, if you don't have this name here, this parameter, you can add it here in add parameter. So I'm going to click heat flux. The number of levels is going to be set as 50 as well, and the appearance is going to be changed to heat flux as well. And I'm going to click detail preview. Okay, we have this, and the heat flux is occurring mainly in the solid material. I'm going to go to display, and I'm going to deactivate the lining. So we are going to visualize this, and I'm going to increase it to 100 levels. Okay, there you have. And you will see that the range in which we are showing this heat flux is between 7,000 watts per square meter. And I'm going to set this maximum level as, I think that's going to be 1 million. Okay. Okay, I think that I'm not going to change it in this well. I'm going to leave it as default. Okay, I'm going to leave it as default, and I'm going to change it in another way. I'm going to click OK, and I don't want to confuse the color table for this temperature and the heat flux, so I will have to change or edit this color table. I'm going to right click on this legend, edit, and I'm going to look here for this color table that is going to be this one here. Maybe I will want to increase this to 100. I'm going to click preview. I'm going to I'm going to change this range here in this zone. So I'm going to specify 100 watts per square meter, and now we have a better visualization here. So the darker color means lower heat flux, and the lighter colors mean a higher heat flux that occurs in the entrance part of the tubes. So I'm going to click OK. So I'm going to deactivate the computational domain, and now we have something like this. The jet color table is going to be for the temperature, and the thermal color table is going to be for the heat flux. Of course, you can deactivate this by separate, and this as well. Okay, now there we have. I'm going to create the flow trajectories in order to visualize what is happening with the temperature profile inside every pipe. So I'm going to select this, and I'm going to select this, and I'm going to set it as 50, and I'm going to change the size to 5, 10 to the minus 6, and visualize. I'm plotting the pressure, but I want to see the fluid temperature, and that's it. Maybe you can increase it to 100, and OK. And if you want to visualize an animation for a steady state, I'm going to click play. I'm going to change it for the velocity, and OK. Now you can see here that the lower temperature occurs near the walls of the pipe, and this is because the fluid, as you know, is in laminar regime, and the higher velocity is observed in the middle of these pipes. Okay, I'm going to deactivate this, and now I have to calculate what is the temperature at every outlet and inlet as well. So I'm going to right click on surface parameters, insert. I'm going to clear this. I'm going to select this surface, and I want it to give me the temperature of the fluid. And OK, I'm going to right click here and show. Okay, and this is going to be called the outlet temperature of the cold fluid. Okay, I'm going to change the parameter that is given here in this table, and I'm going to right click on this head, select parameters, and I'm going to select the minimum, the maximum, and the average, and I'm going to deactivate the bulk average, and that's all. And you will see that you have this average temperature of 314. I'm going to right click again here, insert, and I'm going to specify this phase. Okay, clear selection. Okay, there we have temperature of the fluid, and OK. I'm going to right click in here to show, and we have this value. I'm going to modify the name. This is the outlet temperature of the hot fluid, and I'm going to right click on this head, select parameters. I'm going to deactivate here this, but I'm going to activate minimum, maximum, and average, and we have these values. OK, I'm going to save, and if you want to verify, you can always select the inlet sides. This is going to be this temperature of the fluid. OK, this is the inlet temperature cold fluid. Remember that the top cylinder is the cold fluid. So I'm going to select parameters, and these are the ones that I want to show. And finally, for the hot side, insert. Okay, the fluid, show. Show. Okay, this is the inlet temperature of the hot fluid. I'm going to select other parameters, and that's it. Okay, now you can visualize here or determine what is the change in temperature for every current or every string. Now I'm going to hide this, and I will want to determine what is the heat transfer rate from every and to every surface. So I'm going to click insert insert in surface parameters. I'm going to position on this zone because I want to select the outer surface of this cylinder. I'm going to select other, and I'm going to select the second option that is going to be for me the external surface of the cylinder. So I'm going to select heat transfer rate, and you can also calculate the heat transfer coefficient, but I'm going to specify only the heat transfer rate in this case. So I'm going to click OK, and I'm going to click Show. Okay, I'm obtaining this value, 0.009 watts, and this is going to be heat rate hot. I mean, this is the cold side. And for the other side, that is the hot side, I'm going to do the same. I'm going to clear this selection, select Other. This is going to be this phase. Okay, I'm going to click on this canvas in order to be able to select this. Okay, and heat transfer rate and show. Okay, so the software is determining that this hot fluid is losing 0.010 watts, and this one is gaining 0.09 watts. Okay, I'm going to click OK. Now, in that way, you can calculate or estimate what is the heat that is transferred from one fluid to the another. So I'm going to specify here that this is the heat rate of side. I'm going to hide all of these parameters, and now I want to calculate what is the heat transfer coefficient. So I'm going to clear the selection. I'm going to repeat the operation, but I'm going to select the heat transfer coefficient. Okay, I'm going to show, and I will have these values. You will see that you have a very high maximum heat transfer coefficient value. Remember that this depends on the temperature of the fluid, the temperature of the solid material, and the velocity of the fluid. So in every region you will have different values for the heat transfer coefficient. So this is the heat transfer coefficient for the cold side, and I'm going to determine what is the average heat transfer coefficient for the hot side. So I'm going to select this, look for the heat transfer coefficient, show, and OK. Okay, now you can see that it is the average values are a little bit lower in the hot side, and we're going to create a surface plot. I'm going to insert, and I will determine in a visual way what is the difference in heat transfer coefficient within the actual length. So I'm going to select this surface. So I'm going to select for the heat transfer coefficient, I'm going to specify 100 contours, and I'm going to click OK. So we have this. Later, okay, if you want to change this, you can change it to, for example, 50 or less, maybe 20,000, something like that. Okay, 10,000, 50,000, something like that. Later I'm going to specify another surface plot. This is going to be this side, this one. Okay, this is going to be heat transfer coefficient, the same. Okay, and we will have something like this. Now you can see that the heat transfer coefficient has different values depending on the spatial position. Okay, I'm going to click Save, and later, well, I'm going to hide these values, this as well. maybe we can create some cut plots here. Cut plot, insert. I'm going to change the selection here. I'm going to select for the right plane. I'm going to move it something like this, and I'm going to create the contours for the velocity of the flow and visualize. Okay, and I'm going to set it to 100 contours, and you will have something like this, in which you can visualize you have a laminar regime behavior. Okay, and you can repeat the process. I'm going to clone this operation. I'm going to show, and I'm going to move it to this part. Okay, I think that this is the center of the. Okay, this is the center of every tube. So we can observe that we have a higher velocity here because maybe the temperature is higher here in this side. So save. Okay. Okay, so we have come to the final part of this tutorial. I expect that this is useful for you and that you can apply it to some of your projects. See you in the next tutorial, and thanks for watching.